they are not going to share equally because oxygen is way more electronegative. So oxygen is a 3,5, hydrogen is a 2,1. The difference there is 1.4. And so that difference would put us in that polar category. Atoms in covalent bonds may share electrons equally or not equally. And this is where electronegativity comes in. And I know you memorized that definition. Remember how strongly an atom pulls electrons towards itself in a chemical bond. So we're going to use these electronegativities to predict the type of bond that will occur between two atoms. So if we had, say we had hydrogen molecule, well, that's hydrogen sharing with hydrogen, and they have exactly the same electronegativity, and so they will do equal sharing. But if we have hydrogen bonded to oxygen, such as in a water molecule, they are not going to share equally because oxygen is way more electronegative. And what's going to happen is it's going to pull electrons in that bond physically toward the oxygen in that molecule. And it will do the same thing really on the other side of the molecule. And this is what we call a polar bond. That's the polar bond, unequal sharing. And when we do this, we get a slightly negative end because it's got extra electrons there. They're closer, so that end is slightly negative. That little symbol there is a delta, and that means slightly positive, slightly negative. Not a full charge, but slightly. And so this molecule is actually what we call a dipole. It's got a slightly negative end and a slightly positive end. And the more polar that bond, the stronger that dipole. Now, the geometry of a molecule could actually cancel out these polar bonds affecting the polarity of the molecule. But this is how you identify polar and nonpolar bonds. So here's a little table that will help you. These are some values, and what we're going to do is use our electronegativity. And this is a table that you may find in your textbook, and we're going to take two atoms and find the difference in electronegativity. So these are the values. Chlorine versus chlorine, obviously the difference would be 0, so that's a nonpolar bond. And then we just looked at water and the hydrogen and oxygen bond. So oxygen is a 3,5, hydrogen is a 2,1. The difference there is 1.4. And so that difference would put us in that polar category. Now, let me just say this. These are not cut and dry classes. So it's a continuum. The greater the difference, the greater the polarity of that bond. And then what if we had, look at sodium and chlorine. Sodium is a 0.9, very low. Chlorine is very strong. The difference there is a 2.1. Now, is this a really strong polar bond? No, it's not polar at all. It's actually ionic. The chlorine is so strong that it will take that electron away, not sharing, but a straight up transfer from sodium. And so this is going to help you identify bond type between two atoms. Now let's compare the polarity of some bonds. Fluorine, fluorine in a fluorine molecule, that one's really simple. The electronegativity difference would be 0 there, and so that is a nonpolar bond. And then nitrogen and fluorine, the difference there is a 1.0, so that would be polar. And then oxygen fluorine, it's a little bit smaller, it's about a 0.5, still slightly polar. And then carbon and fluorine, remember our electronegativity trend. The difference between these two is 1.5, and so that is a stronger polar bond. So who is the most polar of these bonds right here? The most polar would be the one with the greatest electronegativity difference. So the polarity of these bonds is going to impact intermolecular forces and a whole lot of chemistry to come. So make sure you get this straight. You can do this.